Hello everyone, in the lecture today, I will introduce the topography, where we will use all the information we collected from the previous lectures to generate the elevation profile. In the topography, we want to draw the elevation profile, which will be the graphical depiction of the elevation change in one dimension. It will show the elevation with respect to the horizontal distance along the path or the route. Usually, the topographical mapping gives the elevation changes and profiles in two dimensions. The figure on the right shows the contour lines for the topographical map. In this map, each contour line represents the locations with the same elevation in the area. This figure shows one example of the topographic map. Basically, if we find that the contour lines are close to each other, then the slope in that region will be steeper. If the contour lines are far apart, then the slope will be gentler. In addition, the spot elevations in the map are height between the contour lines, and they are usually shown in the map as dots with values around them. Now let's see how we can draw the topographic map. In this drawing, we first need to survey many random points about the study area, and then measure the elevation of these points. And during the drawing, it's very important for us to know where each of these points are in the two-dimensional space, and what's the elevation of each point. And then we will translate the elevation over a topographic map. In the drawing, we will select a lot of random points. Then the next thing we have to consider is how we're going to handle these points. Actually, we will use the triangulation technique, which has been widely applied for 3D surface modeling, to connect all those points in two-dimensional space. Actually, choosing the appropriate triangulation for the surface, especially the random points, are very important for the generation of the topographic maps. The wrong triangulation will cause very huge errors in the elevation estimation for the intermediate points in the map. We can take a look at one example in this page to see why the triangulation is so important. The two figures in this page comes from the same data set. We have a set of the random points and we measured the elevation of each one. And then we want to find out the elevation of one intermediate point Q, which is shown at the same location for figure A and B. If we apply the triangulation in figure A, which will connect the point 980 and 990. Here 980 and 990 are the elevations at these 2 points. Then the elevation at the point Q can be interpreted as 985 meters. But if we connect the point 10 and 36, then we can interpret the elevation of point Q as 23 meters. This one is very different from the result we get in the figure A. So we have to determine which one is right for the generation of the topographic map. In this class, we will use the Delaunay triangulation for the generation of the topographic map. In this method, we will first join all the exterior points to create a perimeter around all the points in the study area. And then we will add the interior point one at a time. When the interior point is added, it ends up in the region. The added point is then connected to each vertex that defines the region. After this, the result triangles must be checked according to the rules below. So for each triangle you observed in the triangulation, the circle that encloses the triangle must have no other points inside, and all the vertices of the triangle must be on the perimeter of the circle. We can use the example in the previous page to double check the rule. For the result in figure A, we can use the points 10, 980, and 990, and the circle will be drawn to cover all these 3 points. Then you can find that there isn't any other points inside the circle. So we can claim that this triangulation is not appropriate. While if we consider the result in the figure B, we will use the point 10, 36, and 980, which will generate a very large circle and cover a lot of other points from the study area. Then this one is inappropriate for the topographic map. In the Delaunay triangulation, we can estimate the number of the triangles formed based on the total number of the points n and the number of the points in the parameter. If we are given the two numbers n and k, then the total number of the triangles formed must be 2n minus 2 minus k. Let's check one example to see how we can apply the Delaunay triangulation for the set of the points. The figure here shows a set of random points that we select for the study area. In order to draw the triangulation, we first need to join all the exterior points to create a parameter around all the points, which means we need to first connect all the exterior points. With that, we will finish the first step. Then we will need to add the interior points to the parameters. We will start with the point here. First, we must connect the added point to all the vertices. So we will have the interior lines. And then we must check whether the circle formed by the triangle vertices does not include any other points, except this one. Then we can check the circles generated by the triangles in the previous page. The figure here shows the circles for all the triangles. Clearly, you can see that now the circles will cover the other points in the data set. So we say that this kind of set is correct for the triangulation. Then we will add the second interior points. We find that the second point is actually located in this triangle. So the first thing we will do is we will connect the point to all the vertices in this triangle, which will give us the result here. And then we need to double check the circles generated by these triangles and see whether they are covering the other points in this data set. Based on the analysis, we can see that the circle generated by the formed triangle will actually cover some other data points, which means this kind of triangulation is not appropriate. We need to find the other method to regenerate the triangulation. To correct the triangulation in the previous page, we will first remove the two sides of the triangle that includes the interior points, and then there will be a new region applied for the interior points. We will then connect this point to all the vertices, which will be the lines shown in the figure here. And then we will generate 5 new triangles. 1, 2, 3, 4, 5. We will need to check the circles generated by these triangles and see whether it will cover the other points. By checking these circles generated by the triangles, we can see that none of them will cover the other points in the dataset. This indicates that the triangulation for this dataset is appropriate, and which is able for us to apply it for the generation of the topographic map. With the triangulation that we generated previously, and we are given the elevation of each data point, we will then need to see how to create the topographic map, which means we want to find out the contour lines with the same elevation. Here we assume that along each line of the triangulation, the elevation varies linearly. For example, we have the elevation as 8 at this point and 11 at this point. Then we can divide this one into 3 segments. Actually, there will be 3 equal segments. We will identify the elevation at this point as 9, and this would be 10. For 8 and 9, it could be maintained as 1 point. Also, we can find out the division for the point between 6 and 8, so we have 1.7. We can apply this division for all the lines in the triangulation. With these divisions, we will then connect the points with the same elevation. For example, for the elevation of 10, we'll have the line here, and also we will have the line for the elevation of 9 and 8, 7. Similarly, we can find out another line for 11. And here you can see that by overlaying our triangulation and linearly interpolate for the intermediate elevations along each line within the triangulation, all these contour lines will not crossing with each other, which will be the requirements for the topographic map. If we apply incorrect triangulation for the data, then the topographic map generated for the region will be very irregular, and this one will not be quite realistic. Now let's take a look at one example to see how we can generate a topographic map based on the elevation measured for a set of the data in the field experiment. In this example, we will have a set of locations with the x and y coordinates, and we know the elevations for each point. We can actually use the MATLAB and the engineering program language for the generation of the topographic map with the raw data. In this program, we will first need to import the data that we showed in the previous page, and then we will record the Delaunay function to create the triangulation. After that, we will call the triplot with the purple axis for the generation of the topographic map. In MATLAB, we can import data from Excel or text files. Also, for the generation of the triangulation, we need to create the vertex from the data. And finally, for the generation of the topographic map, we have to create a data grid so that we can draw the contour lines. In the next page, I will show a demo to see how to use MATLAB to create the topographic map. So that's all about the lecture today. Thank you very much for your attention, and I will see you next week for a new topic.